Okay, so this is, I'm barely prepared, so bear with me. So this comes from a little patch we had to write for x264 to deal with some of the stitching problems we have here at Mux. I couldn't think of a name for the talk. I can only think of 3 names. So this is called either Anatomy of x264 patch, aka Be Stitchable does not care about your timestamps. And the slides are not advancing. Or I can't believe we're talking about B-frames again. So I Googled this about an hour ago. So how long does it take a 20-minute YouTube video to process? I didn't do this test myself. I just Googled this, but the numbers seem about right to me, about real time for higher resolution. So you give it a video 20 minutes later, you have your 1080p up. I put the link in the right of where I found this information. Sounds right. I didn't actually test it myself, but that sounds right to me. So what's taking so long? Why is it taking 20 minutes to do this? So this is massively oversimplified. What's happening? So files analyzed, we do some business logic. We then go out and fire off a bunch of transcodes, generate some manifests, and there we go. We got our file. This takes some time. All this stuff is very fast, obviously, except for the transcode step. That is taking all of the time here. So there's ways we could speed that up. We could maybe use hardware encoders, throw bigger CPUs at it, split up the file, try to parallelize it. But the fastest way we know how to do it is just don't do it at all. Just don't transcode it. We know the file, we know the length. We have all the information we need to generate a manifest. So let's just give them a manifest. The problem with this approach, we just now linked to a whole bunch of files that don't exist. So we have, in this example, I'm just numbering them 0, 1, 2, 3, the M4S, excuse me. Well, now we have a problem because you can go and try to play these files and we haven't created them yet. So naive way would be to try to outrun the player, just encode them as fast as we can. But the player doesn't have to play in direct order. And my example here is using 10 segments, but this might be 1,000 segments, and it could require segment 900, and we don't want to wait an hour. So at Mux, and I apologize, it's a little bit salesy for a second, I'll get through it pretty quick. So at Mux, we use just-in-time encoding. So what we try to do is we try to produce a cacheable segment on demand when requested. We can produce these segments in any order, and they have to be stitchable without artifacts or pops, because these segments might be generated hours, minutes, weeks apart from each other. So the bit stream needs to be seamless, and the timestamps have to be perfect when we generate these files to avoid gaps or overlaps. And this gets tricky when you're generating things out of order like that. So I'm talking mostly about the last one today, the timestamps, and specifically video and specifically x264. So go to some code here. Is that showing up? Yeah, that's great. So this is a very simple program using x264 that I wrote. I created this function called encode one segment. It takes a vector of timestamps. I'm just going to step through it real quick. We set up the default parameters for x264. I said it's very slow. I'm enabling stitchable, which sets up the parameters, specifically the PPS, so it doesn't get reset. So every segment can be stitched. I'm setting variable frame rate, which will become an issue in a moment. I'm disabling B-frames for right now. And I'm picking some default values just for demo purposes. So I should probably clear that. These just make it a little bit easier for the demo, but pretty much any values work. But I'm just using this particular settings with 720 by 480 stream, level 3.0, and I'm using a time base of 1/30, but anything should work. Disable logging, actually open the encoder. Finally, I create a frame with just random data, or however x264 initializes it. And then for every timestamp we pass in, we loop over the array. Let me just shrink that. We set the presentation timestamp for the frame to one of the timestamps we passed in. We encode a frame for every frame passed in. When we're done, we flush the encoder because the encoder has a delay and clean everything up. So pretty straightforward. Then our main function, we just encode 2 segments back to back. Each one's 10 frames, numbered 0 through 10, or 0 through 9 and 10 through 19. So I'm going to go ahead and run that. My amazing build system called Bash. All right, so let's take a look at the output. Ignore the DTS for now, but basically we just have our PTS, and here's all our numbers passed in. So 0 through 9 and 10 through 19. There's our 20 frames. Everything looks great. I'm going to go back and enable B frames. Run this again. Sorry, part of my screen's covered up by Zoom, so I have a different view than you. All right, so here we have with B frames enabled. For people who don't know B frames, it's just a way to get better quality out of the encoder by rearranging the frames. So the encoder can encode frames out of order, and as long as they're rendered back in the correct order, it doesn't matter what order they're encoded in the stream. So here we have our same PTSs that we've passed in, presentation timestamps, 0 through 9, except they're in a different order. So there's 0, 1, 2, 3, 4, where's 4? 4 is back here, 5, 6, 7, 8, 9, and then the same thing on our second segment, 10, 11, 12, 13, blah. Okay, so that looks great. So basically this is the timestamps that were generated from the first segment. And just a quick overview of how B frames work, or refresher. We start with a negative timestamp because we're going to start decoding before we start playing back. So at time -2, so the player starts up, it reads the file, and it says, okay, the first time is -2. So it's going to go ahead and decode that frame, but it's going to put that frame in slot 0. So then when we get to time -1, it decodes frame 9, puts that in 9. And this is why we have to have negative numbers, because we have to have a buffer to start decoding a few frames early. When we get to time 0, we can finally display 0, but we're going to decode frame 4 and put it in that slot. And then we just move forward. 1 goes to 1, 2 goes to 2, 3 to 3. When we get to 5 or 4, we already have a 4, so it decodes 5 and puts it forward. Same, we decode 6 but play 5. We decode 7 but play 6. We decode 8 but play 7. And we're done decoding, so we just play out the last 2 frames, and we're at the end of the stream. So from the player's perspective, the segment is kind of shaped a little bit more like this when it comes time to play it. The edges aren't smooth. When we reorder the timestamps, we get a delay at the beginning, and then these frames hanging out at the end. So when we concatenate the segments, they have to kind of fit into this shape and not just be the other shape I showed before. And that's okay here. So this is an example of how the 2 pieces kind of Tetris together. And the numbers work because the top are still monotonic, they're still incrementing, and our presentation order after they've been reordered also increment just fine. The presentation order encoded doesn't really matter too much in this use case, or in this case. Okay. Here comes the problem. What happens if we drop some frames? And that shouldn't have advanced, but. So as I said before, I actually set a variable frame rate. I did not set an actual frame rate. I just want to point that out. And if this is a live stream, we might have a hiccup in the internet. So let's say these 2 frames got dropped. No problem, run that. And this is what we get. So our timestamps look pretty much the same on the first segment, or exactly the same on the first segment. When we get to the second segment, you'll notice we're jumping from 7 to 10, which makes sense. We lost some frames in there. So we move forward through our clock. We go 5, 6, 7. When we get to 8, there's nothing there, but we can still present 8. When we get to 9, we can present 9. When we get to 10, we can decode this frame 10, but there's no frame 10 to play. So we just hold on 9. We get to 11, we can decode 19, but there's no 11 to display, so we display 9 again. We get to 12, and there is a 12 to play. So then we're back on. So we dropped our 2 frames. There was a small little gap, or not gap, but that frame was repeated, and we continue on. Well, there's a problem with this. And the problem is x264 actually treats these two frames, the second and third frames, special. So if we lose these frames and run it, we look at our timestamps or decodes timestamps, we go 6, 7, 6. So now we have a problem because when we get to 7 and we go to 6, what does the player do? It can try to fake it and just keep going. That's actually really hard on media source extensions on the web, because on media source extensions, it tries to set the segments in, because you can intentionally leave gaps or overlaps in media source extensions. So the player doesn't know if this was intentional or not. So this is a big problem on the web. Other players may or may not work. It might look at that and treat it as an error. It might ignore DTS, but some players might have problems too. No matter what, this is a big issue. So as I said, the frame kind of has I've been calling it a shape, and this is kind of what we've generated with this code. So the times overlapped. If you notice though, our reordered PTS actually looks fine, so it should be able to play. It's just kind of the decode side that's confused. What we need is something that looks a little more like this, where it's the right shape, the frames are elongated correctly, but all the timestamps still work. So let's jump back into some code. So how do we solve this? I don't even know what Jupyter Notebook is. What is that? Without going into too much debugging, the variable that turns out to be the issue here is this B frame delay. Now this is the x264 code, part of the just open source library. So what we have is we have our iframe variable, which is just a frame that's incrementing forward for every frame we input. At frame 0, we take this first PTS value and store the PTS from frame 0, which on our first segment was 0, and our second segment was 10. If the frame number is B frame delay, then we set this B frame delay time to be that frame's PTS minus the first frame PTS. So what is B frame delay? We look at B frame delay. It is a simple little equation here. If B frames are enabled and B frame pyramid is enabled, which is enabled here by default, we set it to 2. If only B frame is enabled, we set it to 1, or if not, it's 0. So that's why those 2 frames are special. It's actually looking at those 2 frames to determine how much to back up the DTS at the next segment. Okay, so that clearly means we have to put a value in for B frame delay time that is not determined by the timestamps we pass in. It has to be determined by something else and has to be the same no matter what. But if I showed you before, I have variable frame rate set and I don't have a frame rate encoded at all. So we're basically stuck at this point saying, okay, we need to back up 2 frames, but we have no idea how long a frame is. So what value can we put in this? I gave a little hint earlier. I picked those values special for this demo, even though it would work with any value. Oh man. Sorry, the Zoom stuff is covering my tabs. Okay, I had to unmaximize, sorry. All right, so back to the slides. So in H264, there's a concept called levels, and levels are basically, I don't have a great way of describing it, but it's kind of a maximum complexity. You can say the higher the resolution or the higher the frame rate, the higher the level needs to be. So for a given level, there's a maximum number of pixels per second it can decode at that level. Technically, it's macro blocks per second. A macro block is 16 by 16 pixels. So you can decrease the resolution and increase the frame rate or vice versa. But if you want to increase both the frame rate and the resolution, you will have to increase the level also. So that basically means that there is a maximum frame rate for each level. So now we have something we can get a frame rate value from, even though we weren't specifying a frame rate. There's a maximum frame rate. So I set our value at a level 3.0, which is 40,500 macro blocks per second. Now we need to calculate a new B frame delay time. So I had these values for width and height. We calculate our macro blocks per frame, which we divide the width and height by 16, round those numbers up, which comes out to be 45 by 30, which is 1350. Our macro blocks per second for level 3 was 4,500. Divide that and we get 30 frames per second maximum for this resolution at this level, which is why I picked those numbers, just to make the math easy here. We have a B frame delay time because we have B frames enabled and B frame pyramid enabled. And I set a time base of 1/30, again, just to make the numbers all match. So we can calculate a new B frame delay time by multiplying the B frame delay by the time base divided by blah, blah, blah. It's the reciprocal. It's a simplification of the formula. So that works out to be 2 times 1 times 30 over 30 times 1, and the 1s and the 30s cancel out, and we get 2, which makes perfect sense because x264 wants to delay us by 2 frames. I picked the value specifically, so every frame was exactly 1 tick. So that means our number equals exactly 2. So that's what we're looking for. Let me, jump back into the code here. Sorry, the Zoom window again. I can't tell. Oh, I can look up there. All right, so that script just did a get checkout with the patched version. So here's the modification to that function from before. Now I'm checking if we have stitchable set and VFR set, and we run this. If not, I'm running the old equation just for backward compatibility. But if it is set, we set up some numbers for our numerator and denominator. x264 has this handy built-in table, which is that diagram that I copied and pasted from Wikipedia on the previous slide. It's the exact same numbers, just a nice code format. Here's our level 3.0 at 40,500. Okay, I can't look up there when I'm switching tabs. So we loop over that table, trying to find the row that matches our level that we passed in. Note that if we didn't actually set a level, x264 would have picked one for us when we open the encoder. We take the macro blocks per second out of that table. We take the width and height in macro blocks, which x264 conveniently has already calculated for us. We can reduce that into that fraction. So this would be the, what was it, 45 or 40,500 over 1350. The reduction would come out to be 30 over 1. We run it through that quick formula to get our B frame delay time, which should equal 2. And when we run it, we can see, so our first segment, of course, is still the same, except now when we get to 7, we don't go, thanks, Nick. Now when we get to 7, we move forward to 8, 9 and 10 is missing, and so the frame 9 is held, and that's basically it. So our final result is the correctly formatted segment to make x264 generate stitchable variable frame rate B frame files. Anyway, it was a small little thing I had to dig into to actually solve a real world problem we were having here at Mux. And I just thought it was an interesting problem, the way it interacted with various levels of the spec, and turned into this talk. Thank you.
If this talk goes viral, I'm gonna have to make another alias for your email.
Oh, yeah. Is it? Oh, I totally typed that's not my email address, by the way. There we go. Nick. Yeah, so Nick and I actually bumped into this problem about a year ago. Is that where you're going? Go ahead, Nick, ask your question.
No, continue.
So Nick and I actually bumped into this problem, but we kind of cheated our way through it the first time by disabling B-frame pyramids. So it only gave us a 1 frame gap. And then we were able to hide the rest of that mess just in the garbage that is transport streams. So, but we had to fix it for real for CMAF.
Matt, did you run into any similar issues with the audio?
I am not going to talk about audio in this. Yeah, audio is when we're stitching, when we're doing the just-in-time encoding with the audio stitching, there is some magic happening there, but that I don't really want to get into. But as far as timestamps go, not really. There was an issue with priming samples. Is basically what I don't want to go into, and because it's a whole nother beast. But the timestamps themselves weren't much of an issue.
I had barely an understanding of that, but did you land this patch in x264, and what was that process like?
No, I did not land this patch. So I'm not, we use this here. One, I actually don't know how in x264 because it's pretty clear on like FFmpeg, but like how to patch x264, I looked into it and I couldn't really find the straightforward method online. If I was to land this patch though, I don't know if they would accept that as is, because this, if you were relying on the old behavior, which is why I put all those checks in there, that it has to be B frames and it has to be variable frame rate and it has to have stitchable set. And if you have all of those set, then it would be a change in behavior. And I'm not sure if they would accept that. My guess is they'd want another flag that says stitchable time or stitchable DTS or something, which I'd then check for that flag instead. But since this was used in-house, I did actually release the patch. It's online in GitHub somewhere, but and I did put it into there. I did create a branch in the x264 like repo, so it's there, but they didn't pull it into master because I didn't know what to do after that.
I guess relatedly, you gave a talk about libav. I think that was the last talk you gave at SF Video. Is there, again, rather than this necessarily need to be like a full patch and you're doing things like this, is there a world where you could just be like extending x264 to do this kind of stuff using the same methodology you were talking about then? Or is this the kind of thing that just, you're kind of stuck?
The only other solution would be so you give x264 a PTS and it returns a PTS and a DTS. So you either have to, you only have two options, either change x264 to give you back a DTS you want, or ignore the values it returns and handle it yourself. And that's possible as well. But it's significantly more work to rewrite all those DTS timestamps.
Okay, start here and then over.
Have you tried it with like hardware decoder or encoder, like NVIDIA or something?
This is specific. This patch that I just talked about is specifically x264. Whether the same, so when you pass in a PTS and get a PTS DTS back out, there's no rule in the spec of how to do that. So everyone's going to do it different. I don't know if the hardware encoders will or will not have the same problem. That part of the encode is probably actually, that part of the code is actually probably done in software, probably not open source software, but it's probably done in a driver or something somewhere. I haven't tested it. I don't know what the different encoders would do. I would expect some of them would work and some of them would have similar problems, would be my guess.
What was the efficiency gain versus sort of the first implementation that disabled the B frames and that?
Oh, like the quality and the
efficiency gain, I guess. Yeah.
But what's the, in general, what's the
Like the
efficiency
bit rate
gain
gain,
of enabling B frames? In this, In this particular test, obviously none because it's garbage data. You know, I don't remember what the gain was because when we first did this in production, we just disabled pyramid, like I said, and then kind of hid the slop in the transport stream. And disabling pyramid probably didn't hurt very much, just means B frames can't reference other B frames. I'll be honest, I don't recall. It'd probably be small, you know, single digit percentages would be my guess.
Was there another one over here I saw? Ham, did you have your hand up? No. Okay, good talk. Oh, well, maybe it was you.
So firstly, I thought the talk was super clear and cool. Thank you. I want to go back to your JIT encode. What sort of performance do you get out of that? What's time to first byte? And if you have a 6-second segment, do you start a chunk transfer of the response, or do you have to encode the entire thing before you send it back?
So I don't have the time to first byte offhand, but we do cache segments. So obviously when we encode a file, we cheat a little bit. I said we don't encode. We actually do encode the first couple of segments and just warm the cache. So those are there. But if someone were to skip forward way far into the file, yes, the first person would have a delay of however long that transcode took. But then that's why the stitching is so important, because then that's cached, and that cache lives, you know, whatever days, weeks, months, years. So because of that time to first byte hit only occurs for the first couple of viewers and then just disappears.
Okay, thanks.
But I don't have the exact number off the top of my head right now.
Yeah, and the trade-off there is trying to be able to support like UGC like be able to support the different pricing model, like, you know.
Yeah, you don't have to encode stuff nobody's watching.
Exactly. That makes it so we can try and support the long tail a little bit better, but
yeah, we don't have to support what no one's watching. It's our customers most like it because they can upload an hour video and get a link back within seconds. You know, maybe it might, if someone seeks, it might take a second or two, but then once someone seeks, we do the same thing. We kind of try to pre-warm the next segments. So it's not like it stalls every segment. Someone requests segment, you know, 1000, we'll go 1001, 1002, and then try to get those out there a little bit. And even the same approach can be used to, even if for slow codecs, it's also very useful just parallelizing.
You could, for example, use the Mux demo page, and I don't work at Mux. You could potentially, with that page, check whether or not they use trunk transfer encoding. Last time I checked, they did. And the time to first byte for a segment near the end of that video would be measured in hundreds of milliseconds to, you know, maybe 2 seconds, depending on the rendition.
cool. Anyone else? Going once, going twice. Sold.
This is my first attendance, so it better be a good question or else I'm not going to be invited again. So my name is Saeed and I work for Red Bee Media, which is this global company in video. I was just curious, you keep referring to a problem that you had that you were trying to fix. How was the problem manifesting itself on the decode side?
So
was there a subtle problem?
It depends. In this particular case, as I said before, we were dealing with transport streams, we were able to fudge through it. With CMAF, the reason we could A, fudge through it, and B, there was also a little bit of help from the player there too, because the real problem with this was we're delivering CMAF directly without the transport streams. And the problem there is that the frames would the segments could overlap in the media source buffer, because with media source extensions, you get this infinitely long playback buffer. And then you can put video anywhere you want in it. And it knows where to put that video in the buffer by the timestamps in the file. So if you give it 2 files, media source extensions doesn't assume they're concatenated. So it will put those files on top of each other, or a gap between them or something. So if there's a gap, it's totally, at that point, it's totally up to the browser and the player what happens. So to answer your question, every browser was different.
Okay.
Some browsers played through it fine, because it was only 2 frames. So some browsers were able to just
Yeah.
figure it out. Some browsers noticed that the reordered PTS was actually fine, and it was only the DTS that was messed up, and it was able to play it. And I don't remember which browser. I think it was Chrome actually, but don't quote me on that. Literally just stopped. It just wouldn't even play.
It would be good to test this on a clip with Kittle running with the ball or something like
Yes,
that.
yeah, something like
Then you
that.
could really tell.
Right. But yeah, most of the time it would play or it didn't. There wasn't. I don't recall any that would like macro block or blip or anything like that. Most of them would just play or wouldn't.
Thanks, Matt.
Yeah, thanks. Is that gonna? Oh, hey, look at that.
This stunningly flattering angle up here. I know this bored in the darkness. Cool. Thanks, Aaron, for coming. Thanks, Matt. Again, that was fantastic. We'll try to edit this as best we can to like make this look good. The Zoom was clearly flawless, by the way. I don't know if you all noticed, but clearly the experience. Yeah, the presenter experience looked absolutely flawless. But thanks for sticking through it. But anyway, there's more beers, probably another couple of pizzas. Feel free to hang out. If you're interested in speaking at a future meetup, come grab me over beers. I'd love to have you. Looking at you. Yeah. No, it's okay. You. And yeah, otherwise, thanks for coming, guys. See you next time. Have a good month.